Okay, so today we're going to walk through the entire life cycle of an HVAC project, but we're doing it from the inside, from the perspective of a technical office engineer. We're going to go from the very first drawing all the way to the final handover.
Everything, and I mean everything, starts right here. This is the 2D HVAC shop drawing. You've got to think of this as our roadmap, our Bible for the entire project. Every single calculation, every piece of ductwork we order, every diffuser we install, it all has to tie back one to what's on this drawing. It's our single source of truth.
So, we're going to break this whole thing down into 4 logical stages. First up, the design fundamentals. Then we dive into the detailed engineering and coordination. After that, it's time to hit the site for execution and quality control. And finally, we'll wrap up with testing and the official handover. Let's get into it.
All right, Section 1, Engineering Design Fundamentals. Look, this is the foundation for everything that follows. Getting the stage right isn't just important, it's completely non-negotiable if you want a system that actually works. The very first thing we do is establish the rulebook. This is not guesswork. It's all governed by a very strict set of codes and standards. We're talking about the Saudi Building Code, and of course, the big ones from ASHRAE, standards for thermal comfort, ventilation, and energy efficiency. On top of that, we lock in project-specific data, like the design temperatures and operating hours. You have to get these right, because any change here sends you right back to square one.
So let's make this real with a core calculation. Based on those standards, we figure out our heat load is 90,000 BTU per hour, and we're targeting a 10-degree Fahrenheit temperature drop. So the big question is, how much air in cubic feet per minute, or CFM, do we actually need to move to make that happen?
And there's our number, 8,300 CFM. Now, this isn't just some number we pulled out of thin air. It's the direct result of our load calculations and that design basis we just set up. This single value is now going to dictate the size of our air handling unit, our main ducts, our diffusers, everything.
And this is the part that so many people get wrong. That 8,300 CFM we just calculated, it must perfectly match the equipment data on the shop drawing. Not 99%, 100%. Any difference between your calculation sheet and your drawing is a guarantee for major problems down the line.
All right, on to Section 2. Detailed engineering and coordination. This is where we take those abstract numbers like CFM and start turning them into real, physical, buildable plans that a team can actually work from.
Let's talk about sizing because it has such a direct impact. If you undersize your ducts, the air velocity just shoots up. What does that mean? It means noise and a ton of pressure loss, which makes the whole system incredibly inefficient. The goal is to hit that design velocity sweet spot, around 6 meters per second for main air ducts, which keeps things quiet, minimizes friction, and makes the system energy efficient. Now, sizing isn't just about the physical dimensions. It's also about pressure. We have to calculate the total resistance that the fan is going to have to fight against. We call this the external static pressure, or ESP. It's literally the sum of every little bit of pressure loss in the system, the friction in the long duct runs, the loss on all the elbows and fittings, the drop across the filters and coils, right down to the very last diffuser. This calculation is what tells us if our fan is actually powerful enough to do the job. Once our drawings are locked in and approved, we can finally generate the bill of quantities, the BOQ. And this is a perfect example of how one step depends entirely on the last. The BOQ, which lists every single nut, bolts, and piece of ductwork, is pulled directly from those approved shop drawings. It's simple. You can't have an accurate BOQ without an accurate, coordinated drawing. Period. And before a single piece of metal is cut, we have to coordinate. Look, even if we're only required to submit 2D drawings, we absolutely have to check our work in 3D. We have to make sure our massive ductwork isn't about to smash into a structural beam, a fire sprinkler line, or a row of lights. Finding these clashes on a computer screen is cheap. Finding them on site after things have been built, that's a nightmare that costs a fortune.
And that brings us perfectly to Section 3, Execution and Quality Assurance. Now we're moving out of the digital world of plans and models and into the real world of steel, copper, and concrete. Now here's a piece of advice straight from the trenches. The cheapest price does not mean it meets the spec. When you're buying materials, you have to be relentless about checking the submittals and the supplier's qualifications. Trust me, choosing the lowest bid without verifying it actually complies with the project specs is just a recipe for total disaster. So once the materials are actually on site, the quality control process is really strict and it has to happen in order. First, we inspect the installation itself,
Does it match the approved drawings? Then we run the critical tests. A duct leakage test to make sure our expensive conditioned air isn't just leaking into the ceiling, and a pipe pressure test for the chilled water lines. Only after everything passes do we go for that final sign-off from the consultant and client.
And that leads us right into our final phase, Section 4, testing and final handover. This is the moment of truth. This is where we prove that the system we spent all this time designing and building actually performs the way we said it would.
Commissioning is really all about fine-tuning the system. And as you can see, the biggest chunk of our time is spent on air balancing. That means going to every single diffuser and making sure it's delivering the exact CFM we designed for. We do the same thing with the chilled water system. After that, we run performance tests to check the overall capacity, and then it's time to pull all the final paperwork together.
A project isn't truly done until you deliver what I call the project's legacy. This is a package of critical documents. It includes the as-built drawings that show exactly how everything was installed, detailed O&M manuals for the team that will run the building, all of our testing reports, and of course, the warranties for every piece of equipment. This is the final official record.
So there you have it. From the initial design basis, to the calculations, through the shop drawings and procurement, to installation and finally commissioning. This whole structured, step-by-step process is the blueprint for how professional HVAC projects get delivered. It's not just theory. It's a practical, executable workflow that really works. And that leaves us with one final thought to chew on. The project is done, it's handed over, the system is running perfectly today, but how do we make sure that this finely tuned design is still hitting its performance targets 5, 10, or even 15 years from now? Now that's a question that takes us beyond just project delivery and into the